This question is sourced by AOPS. There are 8 identical lollipops, 10 identical pieces of chocolate, and 5 distinct kids. Each kid must receive at least one piece of candy, but no kid can receive both types of candy. All candy must be eaten. How many distributions are possible? We can tackle this problem by using casework. We can make cases for the kids getting lollipops. One kid gets lollipops, 2 kids get lollipops, 3 kids get lollipops, and 4 kids get lollipops. So let's start with case 1. One kid receives a lollipop. Since one kid receives a lollipop, then there are going to be 4 kids left for 10 chocolates, because that one kid is just going to receive all 8 lollipops. So, since the problem says that each kid must receive at least one piece of candy, then we're going to calculate 10 minus 4 is 6, because we're just going to give each kid one piece of candy to begin with. Now we have 6 pieces of candy left for us to work with. So now this is going to end up being 6 plus 3, choose 3, because of the stars and bars method. There are 6 stars, the 6 pieces of chocolate, and 3 bars to divide it into 4 groups. Choose 3 because there are 3 bars. So that ends up being 9 choose 3, 84. Is that our answer? No, because we have only made this work for the first kid getting 5 lollipops, getting 8 lollipops. What about this kid getting the lollipops? What about this kid? This kid, this kid. So we multiply 84 by 5, giving us 420. That is the answer to our first case. Case 2. 2 kids receive lollipops. Again, now we have 2 kids and 8 lollipops. Again, since the question states each person receives one type of candy, we calculate 8 minus 2 equals 6. Now, using the same stars and bars method, we have 6 plus 1, choose 1. This gives us 7. There's 1 bar and 6 stars. Now we have 3 kids and 10 chocolates. 10 minus 3 is 7, which gives us 7 stars and 2 bars. Choose 2. 9 choose 2, 36. We multiply both of them together because for each one of these choices, there are 36 choices. So 7 times 36 gives us 252. Now, we have to calculate the amount of ways that we can arrange 2 kids for lollipops and 3 kids for chocolate. I've done the calculation here, where we have 5 factorial divided by 2 factorial by 3 factorial. Gives us 10. So 252 times 10, 2,520. Third case. 3 kids receive lollipops. 3 kids ate lollipops. Now we can just calculate 8 minus 3 equals 5. Then 5 plus 2 choose 2 equals 7 choose 2 equals 21. Now we have 2 kids and 10 chocolates. 10 minus 2, 8. Then we have 8 plus 1 choose 1 equals 9 choose 1 equals 9. And then we have 21 times 9 is equal to 189. Again, I've done the calculation here. We multiply the number by 10. 189 by 10 gives us 1890. On to our fourth case. Fourth case. 4 kids receive lollipops. We have 4 kids and 8 lollipops. Since each kid receives at least one piece of candy, 8 minus 4 equals 4. 4 plus 3 because 4 stars and 3 bars. 4 plus 3 choose 3. 7 choose 3 gives us 35. 35 times 5 is equal to 175. Why? Because we know that instead of looking at the ways we have 4 kids for lollipops, we look at the ways 1 kid does not get a lollipop. That's going to be 5. So 35 times 5 gives us 175. So now I'm going to give us our answer. 420, that was our first case. Then 2520, then 1890, then 175. We add all of them, we get 5005. That is our answer. Now at the end, I'm going to say something kind of cool. There, instead of the normal way, how we calculate chooses, like let's say we have 9 choose 4. We know that is equal to 9 choose 5. We would calculate 9 choose 4. 9 times 8 times 7 times 6 over 4 factorial. That would give us 4 times 3 times 2. 3, 2, 18 times 7 gives us 70 plus 56 equals 126. Now we're going to draw Pascal's triangle really quickly. So as we draw Pascal's triangle, we start finding some cool things. Like, I remember seeing this 35 a while back. So let's continue this more, specifically to the 9th row. This is the 0th row, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. We have 2 more rows left. Last row. We have to add 56 and 28. That gives us 70 plus 14, 84. We've also seen 84 before. We had 126. We've also seen 126. This is getting really interesting. Okay, now let's look at something. 9 choose 4 is equal to 126. 9 choose 5 is also 126. Now, we know this is the 9th row. Now let's see what 9 choose 4 is. This is 9 choose 0, 9 choose 1, 9 choose 2, 9 choose 3. 9 choose 4 is 126. 9 choose 5 is 126. Pascal's triangle can let us calculate any choose by just looking at our row number and our column number. So for example, let's say I wanted to figure out 5 choose 3. Now I would just go to the 5th row, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, and I can assure you that it is 10. Let's see. 5 times 4 times 3 all over 3 times 2. 3 cancels out, 2 here, and yep, we get 10. So that's an interesting way to solve this problem. And while it has a lot of casework, and this might seem pretty tedious and annoying, it is still kind of a very good method to solve this. It involves casework and stars and bars.